Hello, welcome to the second part of the recycling lecture series. And in the first series, we saw the numerous processes and pathways which can contribute to emissions as well as energy consumption in primary production. And we also saw how recycling could offer a potential alternative to reduce the emissions as well as energy consumption from the primary production of metals. So continuing along that line, let's go into the fundamentals of recycling. Let's introduce what's recycling. Let's see the terminologies in recycling. And then let's go on to a very important concept of metal criticality. Let's define metal criticality and see how all these things are linked to circular economy one way or the other. So in the introduction to recycling, the definition of recycling, this is, let's say, the accepted very broad definition of recycling. So it's basically the reprocessing of the recovered materials from end of life waste products, so the products that we throw away at their end of life. It's basically taking them and in one way or the other returning them back to the supply chain. So putting them back into action is how you could, let's say, very broadly define recycling. Of course, there are a lot of layers to it, which we are going to see. One important thing is that we contrast between primary and secondary production always. So primary production always means something that is going from the ores to all the extraction processes to the metal and then the product, whereas secondary always mean you take it from, let's say, an end of life waste product or a different sort of scrap. So it is always a material that is produced from a scrap or waste in one form or the other. So that is the key distinction between primary and secondary. Okay, so this is a typical metal life cycle. So basically it is extracted from the ground and it goes into the basic production process, after which you have the flow into fabrication and then into manufacturing, then into use, and then into waste management. Okay, so there are so many things here. So let's take a good look into what they are. Basically, these dashed lines always shows you the losses from each and every phase in the cycle. As you always know that I have indicated so many times that you have losses from different stages. And you have to also notice the discussion that we had earlier, that of the stocks and flows, right? Just to remind you again, stock is something like your bank account and flow is something like your income, right? So here the use phase, they always consider it to be the stock because, you know, it's very interesting to think about it. So for every different material, the way we analyze the stock and flow is going to be different. Because it could be that it's a beverage can in which the use phase is literally, okay, maybe a few days, we just drink it and then we throw it away. Whereas in the case of, let's say, a material that is involved in a building or a construction, let's say a window frame, aluminum window frame in a building, that has a lifespan which is quite long. So they call it a residency period, something that resides in a particular product for a particular period of time. That's the residency period. So for that, like for the buildings, it's half a century. Okay, so always the inflow towards the use phase is going to be greater than the outflow from the use phase, because at any particular point of time you're going to have more material that's going into use than stuff's coming out of use, because of the fact that you have a longer residency time. Okay, that being said, we are going to see about the scrap that is generated, the waste slash scrap that is generated at each and every point of time, and what are the categories of these scrap, so to say. And you have to also notice that in the waste management, it could be many different things. It could be either something that could be taken back and recycled and then the material produced again, or it could be simply lost, okay, not lost, but put into landfills for that particular period of time. Or you have something called as the issue of tramp elements. We are going to see what tramp elements are. Okay, so What are the different types of scraps? It could be firstly a home scrap, that is the scrap that is generated during fabrication or manufacturing. You can remember it as Fabman. It's not some sort of superhero, but it's just fabrication slash manufacturing. So those things which are produced in the early stage of the fabrication or the manufacturing processes, they could be easily directly reinserted through the fabrication process again. So you don't need to expend a lot of energy for that. Or it could be, let's say, a pre-consumer scrap, what's also called as new scrap, but it is generated during more the processes that are closer to finished products than the home scrap. The key point here is that these things can be quite easily recycled, quite easily reinserted. They can be sometimes even remelted and then put back into the production process again. And then you have the old scrap or the post-consumer scrap. So these are basically what's called as EOL scrap, EOL waste, which means end of life waste. So something that you have consumed as a consumer and then you decide to throw away at one fine day, these are the end of life waste. And there are other types of definitions to recycling here. One is called as functional recycling. What is functional recycling? So let's say that you take a product, okay? Usually what they do is that they kind of shred the product, and you can imagine whatever. It could be an LCD TV, it could be a washing machine, or it could be a car. So they shred it, and then they usually separate it into ferrous and non-ferrous fraction, and let's say fines and plastics and so on and so forth. So iron containing material and other type of metals, non-ferrous metals, and plastics and fines and dusts. The key thing here is that, let's say you have a steel, a particular type of steel, austenite. You can take that type of steel, and it's mostly you take that steel and you recycle that steel to produce one or more of specific alloys. So what you're doing here is that you're trying to functionally recycle the steel. You're taking the steel and you're trying to convert it back into the steel. If you are lucky enough, you probably produce the same alloy that was in the waste. Sometimes it isn't possible. So what you do is that you alter the composition of the alloy and you produce a different type of an alloy, but it's still specific. It's still steel in one form or the other. Okay, so that's functional recycling. And then you have what's called as non-functional recycling. So now here we come back to the concept of tramp elements. What are tramp elements? So for instance, copper in steel production is not really, let's say, desired, and usually you have in a lot of products copper being combined together with steel, okay? And it's not easy to get rid of all the copper, because if you want to do a lot of decoppering steps, then you have to expend a lot of energy to get rid of copper completely. So at some point as a recycler, you have to decide, okay, this is an impurity I'm comfortable with because that is not destroying the functionality of my alloy. But the copper that is trapped inside the steel, that is serving no purpose. So that's a tramp element, and the usage of the copper here is downcycled because of the fact that it is present in small quantities in a large quantity of other metals, say here the steel alloy. Okay, so that's non-functional recycling. It doesn't serve a purpose, but it isn't lost, and it is just a tramp element into a large quantity of another metal or an alloy. And then of course you have recycling failures. So you have the things that are not really collected. You have the dust, the effluents, and these are things that are not coming back into the loop. So these are the recycling failures. So here you see a lot of definitions, okay? And then moving on, we are going to define the rates in recycling. That's a real key concept here. Okay, so this is really an important slide, so pay attention. The definitions here has a lot of value because they dictate policies through which we understand recycling and implement recycling policies. So for instance, one of the most important definitions is EOLRR, end of life recycling rate. It refers to functional recycling. So how much of metal that is collected at the end of life goes back to being useful functional metals or alloys is defined by EOLRR. So it's G over D. What's G and what's D? Go back to a couple of slides before. You have all the definitions there. Okay. And then the other important terminology is recycled content. It's a really important terminology. So let's say tomorrow all the mines to produce rhenium, the metal, completely closes. And the only way we could produce rhenium is from the end of life products. That means the recycled content is 100%. So how much of the fraction of input is coming from secondary resources is actually the representation of recycled content. So if you say it's 50%, then it means half of it is coming from secondary resources and half of the metal that is produced is coming from primary metal production. So that's really an important terminology. And you have a lot of other things as well. So the non-functional EOL recycling rate is basically the metals that go into the category of the tramp elements that we discussed before. And the recycling process efficiency rate is simply a definition of efficiency, how much of metal is recycled over how much of metal is actually collected for end of life. One thing you have to see closely here is the end of life recovery rate, in which you have multiple terms here. So you have to have collection, you have to have sorting and the pre-processing step, and then you have end of life processing. So basically imagine you have a collection phenomenon in which you have to collect from so many different resources, let's say for steel, and then you have to separate them into different categories, let's say sort one thing from the other, and then you put it into a smelter, and then you have the smelting process in which you recover the steel. It's quite important here. Okay, so you go on to let's say define and design so smart a metallurgical process in which you have smelting, and the efficiency of that smelting process is so high, then you can at the end of the day still have a very low end of life recycling or recovery rate. Is basically because of the fact that you have collected very little. So this is a really important first step. You have to mandate collection, you have to incentivize collection, you have to make policies to ensure collection of these end-of-life products, so that, and then you can design, let's say, smart metallurgical processes to get as much as you can. But this is a key first step. So why did I introduce all these things? Of course, these are important terminologies and definition for recycling, but also, for instance, the novel battery regulations, let's say the one that EU is currently debating, discussing, and going to introduce soon, has a lot of quantitative targets. So that is how these things are important. For instance, we all know that lithium, cobalt, and nickel, the metals that are in, let's say, criticality, we will discuss criticality later, have to be recycled. So for instance, EU has claimed that you have to recover at least 90% of cobalt from the batteries, and you have to put a recycled content of at least, let's say, 15%. What does that mean? So if you get an end of life waste, the recovery rate should be at least 90% for this particular metal, and the recycled content should be at 15%. That is, that amount of metal that is recovered goes back into production of a new battery. So these terminologies are important because this is how we understand and we design policies. Okay, so here you see the slide in which you have the periodic table and the representation of the end of life recycling rate, which is how much is functionally recycled. So the blue is where you have, let's say, substantial end of life recycling rate, and you could see for titanium, chromium, and few of these metals, the end of life recycling rate is quite high. Especially take a good look at lead because that's also really recycled a lot. But for a lot of these metals, you could see that the recycling end-of-life recycling rate is quite small, especially that of the rare earth elements that you see here, that is the lanthanides, and for even lithium and the things that are used in photovoltaics, such as gallium and so on, cadmium. And it's important to know this because these things are specifically connected to how these metals are used as products. We'll come back to it later, but it's good to know the recycling rates for all these metals. Okay, while we saw, let's say, relatively high end-of-life recycling rates for a lot of metals, we see here for the recycled content, only 3 metals, niobium, ruthenium, and lead has greater than 50%. That is, the secondary production of these metals contribute a lot to the total production of these particular metals. There are a lot of reasons why the EOL-RR can be low or recycled content can be low. For instance, sometimes the collection can be so difficult. Sometimes that, for instance, in the case of lead, the lead is recycled a lot from lead acid batteries. It's simply because lead is primarily used in lead acid batteries. More than 80% of the lead is used in lead acid batteries. And that's why it's easy to mandate a collection system for these things, easy to specifically design a recycling process for lead acid batteries and then put it back as a recycled content into the production of lead as a metal. But for so many other things, let's say these metals such as tantalum in capacitors, they serve really very important purpose, but in the, let's say, in the ocean of waste streams, it's so difficult to collect these particular things because they are present in small quantities in a diffuse and a dissipated manner in a complex and large waste streams. That's why these things are lost, and that's why these things cannot be recycled easily, which means you have a low EOL-RR, but also a low recycled content. But essentially, do not forget the difference between these two, EOL-RR and recycled content, because it's quite important. Okay, let's get into the topic of material-centric versus product-centric recycling. This is an important distinction to make because the UN Environmental Panel prepared this very important report on recycling, and mostly, of course, it's focused on metal recycling, and Professor Reuter and his colleagues prepared it from the perspective of product-centric recycling, which is, let's say, different from the status quo. So what is the status quo, which is what is happening right now, is the material-centric recycling. So what you do is that you collect so many different products and then you shred them, you put it through so many sorting and separating processes such as magnetic separation, eddy current separation and whatnot, and separation based on gravity and so many other things. And then you divide it into ferrous, which is the iron based components, non-ferrous components, and plastics and other type of components, let's say. But the advocacy on recycling is that to move away from this status quo of material-centric recycling that is focusing on iron, aluminum, and X or Y metal, but to go towards product-centric recycling schemes. That is, to consider recycling of a product in its entirety. So for instance, if you take key products such as photovoltaics, solar cells, batteries, magnets, or you could take any important clean tech energy products, right? So all these things have, let's say, multiple different type of metals and different types of alloys, and each one of them serve a particular functionality inside that alloy. So the advocacy is that rather than actually focusing on this status quo of material-centric recycling, let's take a product and let's consider the product in its entirety and design a holistic recycling process from which we could gather all the important metals that are present in the product, and then let's try to go from that back to the product so that we can have this closed loop circular economy. So that's where the advocacy or the policy lies. And also when you have let's say such kind of product-centric recycling, then you have information about how to not just deal with waste or the other type of streams, but also everything that is associated with the recycling process. For instance, sometimes you produce slags from the recycling processes, residues, or you try to minimize the effluents. So how can we actually take these slags or residues and also recycle them in such a way that we can capture value from these streams? But you can also think some steps ahead. For instance, there are many ways to consume a recycled product. One way is that you produce a metal which comes from a product, and then you put the metal back into the same product. That's one way. But also, let's say you produce a byproduct during this recycling. You could take the byproduct and then use it as an input material for some other important functional product. So we saw this example a lot in symbiosis. So this can be again repeated, reproduced in a product-centric recycling. So you see the difference here, right? So material-centric is obviously what's happening right now. And the advocacy is that we move from here towards a product-centric future where we consider everything in a very holistic manner. Let's get into the concept of metal wheel. It's a very interesting concept for, let's say, a complex reason. I'll get back to the complex reason and pose a question to you so that you can think about it. Essentially, it's this. So you see, this is how to say relevant to recycling, but I can also pose the same thing to primary production. The metals which aren't present in abundance, or let's say the minor metals which we don't use as much in quantity, but serve very important functions and used in clean tech devices, they are always associated with mining of the major metals because usually they are present as a complex component in the ores of the major metals. And when you dig up the major metals, you kind of have these processes towards production of these major metals, and in the middle of the way you also try to design processes to recover these minor metals as well. That holds good for primary production, that holds good for recycling as well. So you have this end of life product point of view, and then these are what's called as the essential carrier metals. Okay, so these are, let's say, the backbone of extractive metallurgy, the backbone of the products that we use. And in these metals, during pyrometallurgy, which means high temperature metallurgical processing, or hydrometallurgy, which means low temperature aqueous metallurgical processing, the other metals dissolve in these carrier metals. Let's say if you have these, for instance, let's take lead. In lead, you have the dissolution of all these very important metals, bismuth, tin, and whatnot. And it's the same for, let's say, you can take for magnesium or rare earths, doesn't matter. So you have the major carrier metals, and then you have the minor metals that dissolve during pyrometallurgy, that is noted in this color. And then you have the metals that goes to dust and spice in hydrometallurgy. And then you have the light green, which shows that these are things that are very important in my opinion, but they are part of these major metal cycle. And then you have the mainly recovered element. And then in red, you have really the tramp element. That is the, as I told you, these are, let's say, the elements not only lost, but also they are detrimental to the making of these major metals. So you want to, in one way or the other, get rid of them. So this metal wheel is for you to visualize how these metals are complicatedly interconnected. And what do you do with such kind of visualization? Good question. Let's go to the next slide where I introduce you a complex question. Okay, so At the end of these two slides, I will ask you let's say, a tricky question, and then you have to come up with an answer. I don't have an answer on my own, but let me pose you all the facts, and then you decide. The metal lead is very important because we use it in lead acid batteries, but also the lead toxicity is a known and a major issue, okay? And interestingly, I think people in a journal, Environmental Research, I'm not sure, I think Environmental Research did this digging where they found that, you know, when there is an increase in of lead in paints and gasolines, you have increase in murder rates because lead sometimes is associated with neurotoxicity, lead in blood, and also even robbery and sexual assault. So lead has at least a correlation could be drawn to lead in blood levels and the usage of lead in paints and gasoline and to these really adverse things. And then you see lead is majorly used in batteries. You have, let's say, cable sheathing and gasoline additives and whatnot. But irrespective of the toxicity or the other issues associated with this, the mining has increased over the period of time. So has the metal production, so has the metal use. It has increased over a period of time. And you see here, I think this is a very interesting example of the lead used in gasoline getting decreased, and so is the lead in blood levels getting decreased. So there they found a really nice correlation. And you have not just the release of CO2 and global warming potential from the lead smelting. Of course, that's associated with all metal production, but also 70% of hazardous air pollutants are also associated with lead production. So you have many environmental, ethical, and toxicity related issues to lead. That's one part of the picture. The other part of the picture is where Professor Reuter presents this graphical representation when it comes to lead. See, as I told you in the metal wheel, when you single out zinc and lead as the major carrier metals, you have all these other metals that are minor, that is dissolved during lead smelting, lead production, that always is associated with these lead metallurgy in general. And you have, these are very important metals. You have these cadmium and tellurium that's used in solar cells, the gallium nitride in LED lighting, then bismuth in pharmaceutical. Bismuth is very much related to lead metallurgy, and then you have tin in solars and so many other things. Lead acid battery is also playing a key role here. So his comment is that, see, if you want to just ban lead, do a blanket ban on lead, what happens is that we are moving from, let's say, a carbon intensive economy towards decarbonization, right? And this journey towards decarbonization is inevitably based on usage of metals. Okay, this much is very straightforward. And we need all these minor but very functional metals to serve us, to give us the clean tech devices which can combat the issue of climate change and move towards decarbonization. And in this journey that we are embarking towards a circular economy, by banning a blanket banning lead, you create this gap in this cycle, and we won't be able to drive this vehicle of circular economy of metals, is the comment from Professor Markus Reuter. And chemically speaking, in terms of the metallurgy, it is true. You also have a lot more of other issues associated with it, because sometimes people, for instance, I will give you one example. EU has a policy of not sending away the used lead acid batteries to countries which don't have the capacity to recycle. Fair enough, but also the EU guarantees this. But the countries which do have the capacities to recycle also can immediately send it over to other countries which couldn't care or don't have the resources to recycle lead, and eventually the lead acid battery waste from EU can end up in another country in the global south where you have increase in lead toxicity because of how the let's say the middleman didn't manage the issue correctly. So environmental issues are abound. A lot of environmental issues and other issues are associated with lead metallurgy, but also it plays a very crucial role in terms of being a carrier metal in circular economy. So Professor Reuter's comment is that we shouldn't be blanket banning lead, but we should be carefully managing lead, carefully controlling all the processes and avoiding dangers and ensuring that there should be no affecting of this toxicity on so many other things. I think like there are, even now, I think there was an interesting discussion, I think in EU Parliament or somewhere, where they tried to ban lead in ammunition, in bullets, where they use it to hunt birds. And even this was met with stiff resistance. Even though this passed, it was met with stiff resistance because people felt that the lead bullets are in fact easier and cheaper to get, and they did want to use lead even in bullets. So I present you all the facts with all the pictures from all different sites, so you come to your own conclusion of how do you go ahead with building a circular economy together with lead metallurgy, or avoiding lead altogether. How do you want to face this issue is something you ponder about, you think about. Okay, we saw already limits to primary production, where we found that it is associated a lot with emissions, is associated a lot with energy consumption. So we found that, okay, recycling does give us a lot of benefits. Well, what are the limits to recycling? There are many. So for instance, the first thing you saw from the end of life recycling rate is heavily dependent upon the collection rates. Unless and until you mandate and you introduce norms to make sure that things are collected, sorted properly, unless you make regulations, rules, legislations, things won't be collected and things won't be sorted properly. Okay, there is enough collection and sorting happening now, but there are a lot of improvements that could be made. So collection rate is a real impediment to meaningful recycling. And you also have this informal economy where a lot of these wastes, plastic, metal and whatnot, especially the waste electrical and electronic equipments, we still have the issue of illegal exports to global south countries. Okay, and then as I always tell, there is no free meal, actually no real free meal. At least you always have the second law of thermodynamics. What do I mean by that? See, we are increasingly using complex product to make our lives comfortable. Of course, it does enhance the lifestyle, the benefits, but we are using so many different alloys inside one product, and even recycling one alloy is already complicated. Would you like to spend infinite amount of energy and resource and materials, so much so that you could recover the most minor but valuable metal from this particular waste stream, or would you rather not do it? So with always increasing entropy, with energy losses that is associated with every step in recycling, it goes to some extent to certain point where it is more energy intensive, more resource intensive to recycle or to recover particular metals from a complex product than to even produce it primarily. So it gets to that point because of the fact that we are building up very complex products. That is where designing these products to recycle comes into picture, and it's a very important solution. See here, for instance, let's say if the return rate is basically the recycled content, right? So how much of the percentage of recycled content is going into the production of metals is basically return rate. So with increase in return rate, with more and more materials coming from secondary processes, from recycling processes into the production of, let's say, metals, you have the energy for primary production going down. Because of course, if you go to 100% from recycled content, you have nothing from the primary production, as you could imagine. And then you have, of course, the energy for reprocessing slowly increasing. That is also given because of the fact that you have complex waste and the volume of the waste increases, which means that the energy for reprocessing also increases with the recovery rate or recycled content. But see here something happening with energy for collection and sorting. First, you have this normal linear increase, after which you have some sort of an exponential increase with increase in return rate, with increase in recycled content. Why? Because more and more materials have to be transported from all the different places to recycling plants to actually recycle. So here is the thing, with increased recycled content, that is the amount of material in production that is coming from recycling. So secondary production of material, secondary resource-based production of material. With increase in recovery rate, with increase in recycled content, first you have a linear increase, but at some point of time, it's going to go bonkers in a sense that you are going to have a lot of issues associated with the transportation, and the feed is going to get infinitely more complex, which means to collect that and to sort it from one from the other, it's going to take a lot of energy. And that's why you see exponential increase in energy with increase in return rate. Once again, return rate is basically simply recycled content. So you could go back to the definition and understand it again if you didn't get it in this slide. And of course, with total energy, if you plot it, it goes somewhere around like this. So you see, it's basically, it has some sense and some sort of association with the second law of thermodynamics. We want to get more recycled content, but it is associated with so many other different issues. Because I talked about residency time, right? Imagine you are using it in a product like a magnet in a wind turbine, which doesn't come out for 30 years. Then you don't have a lot to gain recycled content because a lot of it is in the used phase. And if you want to infinitely increase the recycled content instead of completely shunning the primary production, and if you still want to make more and more complex alloys, that's going to cost you in energy. That's all this graph says, okay? And other factors are incomplete liberation. Liberation is basically separation of one material from the other, right? So more complex the feed is, very difficult it is to separate one thing from the other, okay? And very importantly, see, recyclers, I'll come back to this particular point that I'm saying in the legislation slide. Basically, recyclers target value, okay? So what they target is that what is the most valuable metal that I can easily recover, or valuable thing that I can easily recover inside a complex stream. They don't target a volume. You have to dictate policies for them to target volumes, because say there is a lot of waste. They don't want to use or like deal with a lot of waste simply because it's mandated. They want to recover as much as metals from a low volume of waste so that they can stay afloat profitably. So that's a key issue with the economic perspective in recycling. So how do you deal with it? How do you mandate recyclers to deal with high volumes as well as, let's say, keep them afloat in economically? That's a very challenging and interesting topic altogether. So having said all these things, let's come to the very, very important topic of metal criticality. This is important topic because I'll come to the next slide, and tell you why it is important. It's the reason why you are listening to this lecture in a roundabout way. This is the reason why you are listening to this lecture. See, Professor Gradle is a very important, let's say, person in industrial ecology, and they started out with the question, which metals are very critical, that is, we should be very concerned about. And you already know that concern is a vague notion. So you can be concerned for many things in life, but you have to clearly understand why something makes you to be concerned. That's why they came up with this plot with different implications. and found out why we need to be concerned about some set of metals. There are three axes here. So you have the vulnerability to supply restriction. So imagine that one country has monopoly of production of a particular metal, and that is coming under, let's say, the susceptibility part. And you have the metals being in use in a type of product where substituting that particular metal is not so easy. And it is of great importance sometimes to national security interests or other things. So all these things put together are basically vulnerability to supply restriction. To put it more bluntly, sometimes one country's army wants to hold back that particular metal because they know that it's used in weaponry in other countries' armies as well. So that also happens when it comes to supply restrictions. And you have supply risks. It could be that you have sometimes a geopolitical war and then you encounter a supply risk. And then it's also geological. That is, sometime you have particular metals present exclusively in some areas of geography, and it's simply not available everywhere, and that becomes also supply risk. And then you have environmental implications. This part, I think it's easily understandable. So with all these things, what they did was they found, actually it's not so important, but I'll just tell you what they did. So they found a scale from 0 to 100, and they averaged out for all these things for supply risk, environmental implications, and supply restrictions. And then they found a common average, and then they plotted this diagram of metal criticality. This is how they define criticality. So now EU and other countries, including US's Department of Energy and China and all these countries, have started defining critical metals. And EU releases, I think, periodically the list of critical metals. I think when I started in 2014, there was a list, 2017, there was a list, and I think they released a list in 2020. And they added lithium, graphite, and other stuffs to it as well. So what you see here is that different metals present at different level of criticality that they try to plot. So some are more having more implications on the environmental side, some more on the vulnerability, and some more on supply risk. So Gradle's criticality definitions come with these three important points. Professor Gradle talks about high companionality. What does that mean? It means something that I explained to you 2 slides before. Some metals are major carriers and other minor metals are simply associated with it. So you see, these metals which are critical can have high companionality. That is, they are not produced in large quantity. They are not iron, aluminum, copper, nickel, or zinc. They are some minor metals. They are associated with other major metals. They have very high companionality. And they aren't used in a lot of quantity. They are used in minor quantities, but used in important application. And there are no suitable substitutes for these metals. I cannot simply switch iron for an aluminum for something else and then still the product works. Sometimes some metals don't have a lot of substitutionality. So how do we solve these things? There are many ways, of course. It's a shame that I spelled recycling badly in this particular slide. So it is, of course, one way is to recycle, and the other way is to find out sometimes if you can substitute an entire alloy for something. I think in aerospace they used a lot of rhenium. Then they ran into a huge issue of supply risk, and then they tried to come up with a whole new alloy. So that's how they tried to solve it. So you could do substitution, you could do recycling, and there is also another thing that Professor Gradle doesn't mention, but I think that's also a possibility. Maybe try using less things. That's also not so bad. Okay, this entire slide is the reason you are listening to this lecture. Why? Because in 2010, China increased the price of rare earth elements 10 to 15 times. These rare earth elements are basically lanthanides. You know, in the periodic table there are lanthanides and actinides separately in 2 different rows in the bottom, right? So the lanthanides are basically having a lot of these. Lanthanides are rare earth elements together with scandium and yttrium. So what happened was these rare earth elements, neodymium, praseodymium, dysprosium, which are used in magnets, which are very critical to so many electric applications, and they are used in windmills and so many other clean tech devices. And China had, they still have a monopoly over production because of so many reasons. Partly the occurrence of metals occur in China, partly they have, let's say, very sophisticated and a huge infrastructure for producing these complex metals. And in 2010, there was let's say, a tug of war between China and the EU and US over rare earth elements in the World Trade Organization, and they had a legal dispute. And due to this ban of exports of REEs, rare earth elements, or the prices increasing 10 times, 15 times, both EU and US wanted to counteract. One part of it was a case in WTO. The other part is EU tried to recycle these metals from end-of-life waste. EU wanted to have security over their supply. So you see here in this graph between supply risk and economic importance, these rare earth, light rare earth elements and heavy rare earth elements are really at the top in terms of supply risk because of apparent monopoly of these metals by China. So you could see how important these metals are in terms of creating recycling initiatives. So much so that you listen to this lecture because I got a PhD position in the Netherlands 6 years back due to the fact that there was a rare earth crisis. EU tried to create so many recycling projects for rare earth elements. And I was chosen as a PhD student to focus on recycling these rare earth elements from the waste. And then, yeah, I got this position again in recycling. So you could see that for recycling, criticality is a huge component. So without it, maybe there would have been a lecture in a different sense, but this particular thing wouldn't have happened. So criticality is a very important concept, and the criticality is also a driver for recycling in many different cases. There are many other drivers, but criticality is definitely one of them. Okay, this is actually a really important paper. Please pay attention. So the researchers in this article tried to answer the question, is lithium critical? It's really a simple question, very complicated answer to actually get. I think we all know that if you want to decarbonize meaningfully, you have to decarbonize the transportation sector, okay? You're going to hear a lot about battery electric vehicles. Okay, sometimes you'll also hear about fuel cell vehicles for transportation, but maybe listen less to these fuel cell selling people, especially when it comes to transportation. It's my view, but I can substantiate it with many different facts. Anyways, so you are going to hear a lot about battery electric vehicles, and lithium is a really important component in battery electric vehicles. Okay, the view from a lot of people in mining sector, I even read a post today as we speak, is that we have abundant supply of lithium, almost a continuous supply, that we don't really need to bother about lithium's criticality or lithium scarcity or whatnot. Is that true? That's an important question to ask. This article was published in 2020 in Nature Communications, pretty good journal. They assessed almost 18 scenarios with giving weightage to a lot of different factors to see so many different supply and demand scenarios, and they included if we recycle, how much of lithium we can get, if we exploit so much of primary resources, how much of lithium can we get. One important thing is they put it, and they did it for the whole century. Okay, always have a long-term view. They also did it for short and medium term, but the implications are of course long-term. And I want to read a sentence to you which is very important. The results show that lithium availability will become a serious threat to the long-term sustainability of the transport sector unless a mix of measures is taken to ameliorate the challenge. Okay, such an important sentence. If somebody tells you that We have everything in abundance and we don't need to worry about availability. Always be very careful in listening to that and take complicated factors and facts into account because it's important. So what do they suggest as ameliorating measures? They say that reduce the dependence on the vehicles in general and the lithium batteries by promoting improved public transportation, shared rides, and other possible solutions. So coming back to the whole concept of lithium criticality and recycling, connected back to the circular economy driving solutions, not just in a superficial way saying that, oh, using renewable energy, using batteries as grid storage, batteries for transportation simply promotes circular economy. No, always connected to the underlying scientific rigorous facts and phenomena. Here, when you talk about car sharing in a way, let's say amounting to dematerialization, and then talking about performance economy, where you have the services being at the center of such kind of economy. This is what you need to take into consideration by promoting public transportation, by promoting rights, sharing rights. You actually try to reduce the dependence, then you combat the criticality, and then by including recycling, you do all these things together. So the second point is recycle the produced lithium-ion batteries to ensure that you have some sort of combating towards the, let's say, the criticality problem. And improve the battery technology to reduce material demand per battery capacity. What do they talk about here? Dematerialization, of course. Substitute demand for lithium batteries by developing new battery chemistries. You have sodium ion, magnesium ion, calcium ion, lithium sulfur, lithium ion, so many other battery chemistries that you could actually come up with. So substitution is the keyword here. And then replace demand for batteries by developing sustainable transport options that do not require batteries. Can we actually imagine a different kind of transportation that we don't actually require batteries? So all these things, important 5 points, concerns the answer to the criticality question of lithium. Okay, we are done for the lecture for today. So following up these lectures, we'll talk a little bit about how to recycle the waste electrical and electronic equipments in general. We will have some schemes. At that point, I have to talk a little bit about metallurgy. I'm sorry about this, but yeah, I'll try not to make it super difficult, but I think you do need to understand some flows, some flow sheets of how these metallurgy works. Try to make it fun by maybe including videos, but we will have to learn about some of the recycling techniques at least. And then I'll give you some product-centric examples, I think mostly batteries. If you are interested, I can throw in a complex problem when it comes to batteries as well. A lot of ethical, social issues are there. I can try to present you all these facts and could be interesting for you guys together with the metallurgical flow sheet. So all said and done, that's it. Good luck, and let's see for the next lecture.